This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll see the operation of carry look-ahead adder. So first of all, let us discuss about the limitations of binary adders, and we'll see the carry look-ahead operation and the logic circuit for implementing the carry look-ahead operation and the advantages of carry look-ahead adder. So first of all, let us see the drawbacks or limitations of binary adder. So the binary adder, we have seen that whatever it is a type, either it is a serial adder or a parallel adder, there exists some propagation delay. So that means in case of serial adder, the addition is performed bit by bit and hence the delay is more. Whereas in parallel adder, even though all the bits are applied to all the full adders at a time, there exists a delay due to the propagation of carry from one section to the other section. So that is due to the cascading of number of full adders. So as the number of full adders or else number of bits to be added increases, the delay of carry propagation from one section to the other section also increases. So that is the major limitation that we can observe in parallel binary adder. So here the following method, by following the method, some of the methods, we can get the high speed in parallel adder to produce the binary addition. So that means by using some technology, some mechanism, we can increase the speed of binary addition. What are the mechanisms here? By employing faster gates to reduce the delay, we can reduce the propagation delay, but there will be a capability limit for every physical logic gate. So that means here we can increase the speed of parallel adder by just using the logic gates with reduced delays. So that means we can use logic gates which can have less delay so that the carry propagation can be done faster. So but here there is a limitation again. So each gate, each physical logic gate is having a limit for the delay also. So that is the major drawback again here. So the next one is the carry look-ahead adder. So another way is to increase the circuit complexity in order to reduce the carry delay time. So in first way is to use the gates with reduced delays where we can have some limitation. That means every physical logic gate is having their own limitation of delay. That is why we are going for the another mechanism, that is in another way what we are doing, we are increasing the circuit complexity in order to reduce the propagation delay. So there are several methods available to speed up the parallel adder. One commonly used method employs the principle of look-ahead carry addition by eliminating the interstage carry logic. So what is another way? So in another way, we can also reduce the propagation delay by using another principle which is called as carry look-ahead addition process, and there which can eliminate the interstage carry logic. That means where it can eliminate the propagation of carry from one section to the other section so that the delay can be eliminated. So that means well in advance we are going to generate the carry, and also we are having a mechanism for making that carry to propagate from one section to the other section. So that mechanism is included in carry look ahead principle. So what is that carry look ahead principle? We'll see now. So carry look ahead adder is a fast parallel adder as it reduces the propagation delay by more complex hardware. So it is having a drawback. What is that? It increases the circuit complexity, but it increases the speed of operation. So as it increases the circuit complexity, so it is also costlier. But where we require in some applications, we require to perform the addition operation as fast as possible. In such cases, we can use a carry look ahead adder, even though it is costlier and it is complex also. Okay, so the carry look ahead adder is a fast parallel adder as it reduces the propagation delay by more complex hardware, and also it is costlier. In this design, the carry logic over fixed group of bits of the adder is reduced to two-level logic, which is nothing but a transformation of the ripple carry design. So what we are doing? We are going to design a ripple carry adder over a fixed group of bits. So here in this method, we make use of logic gates so as to look at the lower order bits of the augend and addend bits to see whether a higher order carry is generated or not. So we need to always look at the lower order bits in order to see whether the higher order carry is generated or not. So here, this is a basic full adder circuit which we are using for generating and propagating the carry input. So full adder circuit, as we all know that it requires 2 XOR gates, 2 AND gates and 1 OR gate. So this is a full adder. So where this is the input to the first full adder, first XOR gate is AIBI, that is AB, and it is the propagate function. Okay, and this is the generate function GI, and finally the output is, some output is taken across the other full adder, that is XOR gate. So next, the carry input to the next section is generated from this output of this OR gate, that is CI plus 1. So at each and every stage, we are going to generate a carry, propagate and generate function. So from this logic circuit, we can see that the propagate function is given by A XOR AI XOR BI, let us consider. Whereas similarly, carry generate function is given by GI is equals to AI into BI, or else AND of AI BI. So the truth table of logic full adder circuit. Let us see the truth table of full adder circuit. So as we all know that full adder is a circuit which can add 3 bits of data at a time. That is 2 single bit numbers and 1 carry input. So these are the 3 inputs here, A, B, C, I. So 0, 0. So I'm just considering the carry input only. So when I'm adding these 3 bits, 0 plus 0 plus 0, I don't have carry. So that is why carry output is 0. So 0, 0, 1. So again the no carry. So I'm not considering the sum output. I'm taking only the carry output here. So full adder, it is performing 0 plus 1. It is 1. 1 plus 0, 1. So is a carry generated here? No. Here also no carry generated. And next 0, 1, 1. So 0 plus 1, 1. 1 plus 1, 0 with a carry 1. So carry is generated. Next 1 plus 1, 0, 0. So 1 plus 0, 1. 1 plus 0, again 1. So again in this case also no carry generated. So carry is 0. So 1 plus 0 is 1. And 1 plus 1, 0 with a carry 1. So carry is generated. Now 1, 1, 0. So 1 plus 1, 0 with a carry 1. So carry is generated. And 0 plus 0, 0. Sum I don't care. I'm just taking the carry output. So 1 plus 1, 0 with a carry 1. And 0 plus 1, 1. So carry is generated. So this is a carry. Right? So here, now if you look at this one. So even though we have carry input here, no carry is generated. No carry is generated. So whereas in this case, we have carry. So this is 1, whereas this is 0 and this is 1. So no carry propagate, whereas this 1, 1, 1, both are carries here. So it is carry generate function. So this is no carry and no carry propagate, and this is carry generate. So here in this case, so if you see that what is the function we have, Pi is equals to Ai XOR Bi, whereas Gi is equals to Ai into Bi. Now if you look at this one, 0 XOR 1. 0 XOR 1. Okay. So 0 XOR 1 is 1. Whereas 1 XOR 0 is 0. Sorry, 1 XOR 1 is 1. Okay. And, but here the carry is generated, but it is not propagated because I have got it as 0. The propagate function I have got it as 0. So that is why I am saying this as carry propagate. Whereas carry generate, why I am saying it as generate here? AIBI, 1 into 1, 1. Whereas 1 into 1, again 1. So that means it is a carry generate function. Whereas this one, 0, 0, 0, no carry generated. 0, 0, 0, no carry generated. 0, 1, 0, no carry generated. If the carry itself not generated, then what about the propagation? The carry will not also be propagated. So that is why here no carry generate, no carry propagate, and carry generate. So this is the truth table of full adder, and based on which we have understood the carry generate, carry propagate conditions here. So as we have the equations here, so at every stage, irrespective of the carry input, we can have the carry generate and propagate function. So now for deriving the truth table of this adder, two new terms are introduced, that is carry generate and carry propagate. Okay, so the carry generate GI is 1 whenever there is a carry CI plus 1 is generated. So wherever there is a carry generated from CI plus 1, then there exists a carry generate, right? Now coming to the depends on AI, it depends on AI and BI inputs, right? So as I told you that carry generate function is AI into BI, right? So when GI is equals to 1, it indicates that when we can get GI is equals to 1, depending on AI and BI value, the generate function becomes 1. So that is why it depends on AI and BI inputs. And GI is 1 when both the inputs AI and BI are equals to 1. That just now we have seen the truth table. So hence GI is calculated as GI is AI equal to AI into BI. Now coming to the carry propagate. So carry propagate PI is associated with the propagation of carry from CI to CI plus 1. And it is calculated as PI is equals to AI XOR BI. So this is the carry propagate function. So this propagation function is associated with the carry of carry propagation from CI to the CI plus 1. That means one section to the other section. In order to make the carry to propagate from one section of full adder to the other section, we always use the propagate function. So the truth table of this full adder can be derived from modifying the truth table of full adder. That means the carry look ahead adder truth table can be obtained by just modifying the full adder truth table. So using generate and propagate terms, the sum and carry terms are given as below. So here this based on the sum and carry. So as we have seen the logic circuit, so we can write the sum output as, so this is PI, right? So sum output is equals to PI XOR CI, right? PI XOR CI. Whereas carry output can be obtained as, what is this one? This is CI, whereas this is PI. So PI into CI, and this one is GI. So that means CI plus 1, I can write it as GI. CI plus 1 is equals to GI plus PI into CI, right? So that means irrespective of the waiting for the carry from the previous section, I can generate this propagate and generate function by the inputs given at a time. So here, if I know CI, how can I get CI? I can get CI from the carry input here, the basic carry input, and I can have PI. What is PI? That is AI into BI. Okay, AI XOR BI. So like that, we can have all the carry inputs at a time. Let us see how we can get all the carry inputs at a time. So here these are the equations for getting the sum and carry output. SI is equals to PI XOR GI and CI plus 1 is equals to CI into PI plus GI. So now, first of all, therefore, the carry bits C1, C2, C3, C4 can be calculated as. So in the previous case, parallel ladder case, in order to generate C2, I have to wait for C1. And in order to generate C3, I have to wait for C2. Again, C2 is depending on C1. To get C4, I have to depend on C3 and C3 is depending on C2 and C2 is depending on C1. To avoid this delay, so we are having our own carry equations irrespective of the time. Whenever the inputs are applied, all the carries are generated at a time. So this is C1. So by substituting the values in the equation, so Ci plus 1 is Ci into Pi plus Gi. Ci plus 1, C1. So that means I value is considered to be 0. If I substitute I is 0 at this one, so what I'll get? I'll get C1 is equals to C naught P naught plus G naught. C naught P naught plus G naught. Where C2. How can I get C2? C2 means I is equals to 1. So if I substitute I is equals to 1 in this equation, C2 is equals to, I is equals to 1. So C1 P1 plus G1. Okay, plus G1. So how can I get P1? So P1 is equals to what? A1 XOR B1. Whereas G1 is equals to A1 into B1. So am I waiting for any C1 here? No. Where C1 can be obtained, C1 can be obtained by substituting the values here. So these values I can substitute and I can get these values. Where P naught is equals to what? A naught XOR B naught. And G naught is equals to what? A naught into B naught. So as I know all these values, by just simply substituting, I can get the C1 and I can also get the C2. Similarly, C3 can be obtained like this. And I'm substituting this here. Okay. Now, C4 is equals to C3 P3 plus G3. Where C3 can be given by C0 P0 P1 because the C1 is equals to C0 P0. So first of all, here we know already C1 value. What is C1 value? C0 P0 plus G0 plus G1. So I can simplify this one as C0 P0 P1 plus G0 P1 plus G1 plus G1. Just substitute this in this equation. So here C2 is C0 P0 P1 plus G0 P1 plus G1 into P2 plus G2. So what is this one? If I simplify this, what I'll get? C0 P0 P1 P2 plus G0 P1 P2 plus G1 P2 plus G2. So this is my C3. Now I'm substituting this C3 in this one. So if I substitute C3 and simplify this, I'll get this equation. Right? So this is the equation for C0, C1, and this is the equation for C2, this is the equation for C3, and this is the equation for C4. Okay? So from the above Boolean equations, we can observe that C4 does not have to wait for C3 and C2 to propagate, but actually C4 is propagated at the same time as C3 and C2. Since the Boolean expressions for each carry output is the sum of products, so these can be implemented with one level of AND gates followed by an OR gate. So C4 does not have to wait for C2 and C3 to propagate, because by looking at these equations, what we can see, we can implement all these by simply using logic gates, that is AND and OR gates. Once this implementation is ready, so just apply the inputs, then you can have all the carry outputs at a time. So that is the logic function, the implementation of all the carry outputs of the carry look-ahead adder or else using the carry look ahead principle is this one. So where again P3 G3 can be implemented using again logic gates. What are the logic gates here? This is XOR gates. Okay, so that is A3 XOR B3, and this one is A3 into B3. So again this can be available with the one more logic gate like XOR and the gate. Okay, so this is how we can have all the carry, all the levels of carry, that is C1, C2, C3, C4 at a time, such that the propagation delay is reduced. Even though the circuit is complex. So this is all the extra circuitry which we require to generate all the 4 carries at a time. Okay, so that is how the circuit becomes complex, but at a time once I apply the inputs, I can able to get the all the 4 carries. So I could reduce the propagation delay. So this is the carry look ahead, carry generator. Okay, so now therefore a 4-bit parallel adder can be implemented with a carry look ahead scheme to increase the speed of the binary addition as shown in figure. So this is the 4-bit parallel adder with carry look ahead generator. So here this is the C out. Okay, so here if you see, this is carry A1 B1, and this is NOR gate and NAND gate. So, and A2 B2 NOR gate NAND gate, A3 B3 NOR gate and NAND gate, A4 and B4. These are the extra circuitry. These are for generating and PI and GI. This extra logic gates are used to generate the and propagate to implement the carry, propagate and generate function. And by cascading all the stages, we can have the carry look ahead adder. So this is the carry look ahead adder circuit with carry look ahead scheme which can generate all the 4 carries at a time in case of 4-bit parallel adder. Okay, so what operation it is going to perform here? So here these are all the this is inverted. This is a bubble at the input side indicates that particular input is inverted. So like that, so we can have this complex circuitry, but the thing is we can have the carry, generate and propagate function at a time once the inputs are all applied. So, and hence we can get the all the 4-bit sum and the carry output at a time without any propagation delay. So this is the implementation of 4-bit parallel adder using carry look ahead scheme. Okay, so like that you can have either 8-bit or 16-bit or 32-bit full adder also, parallel adder also. By just cascading this 4-bit parallel adder, we can have, so this is we can have 16-bit, 8-bit or 16-bit or 32-bit parallel adder by just cascading a 4-bit parallel adder using carry look ahead scheme. So this is about carry look ahead adder. So now let us see the advantages of carry look ahead adder. So in this adder, the propagation delay is reduced and the carry output at any stage is dependent only on the initial carry bit of the beginning stage. Using this adder, it is possible to calculate the intermediate results also. So this adder is the fastest adder used for the computation like addition or subtraction. So this is about a carry look ahead adder. I hope it is clear to you all. So by using this carry look ahead adder, we can implement fast parallel adders such that the propagation delay is reduced, but the complexity of the circuit is more and it is costlier also. So it is mainly used for the application where the fast computation is required. So that's all for this lecture. Thank you one and all.
Like, share and subscribe. Hit the bell icon for more updates.